All right. We'll be going through this paper. And it's the 2024 test one, 360 organic chemistry. So Copperbelt University Department of Chemistry, whatever stuff like that. You all know this. So I just got the paper. So the content is. So this is what was in the paper. All right. So these are the question we have: the electromagnetic the spectrum, these Woodward compounds. We have sulfonation, different chemical reactions. So I've typed them. I've decided to type all these questions, and we'll discuss them one or two, and we'll see how we can actually. I'll concentrate much on saying, I mean, explaining than writing. All right. So we can start. So the first question we have is, what is electromagnetic spectrum? Discuss how UV spectral visible spectroscopy assists in determination of concentration in organic compounds. So we'll see. Let me explain this. So what we need to know is that I won't explain this, but electromagnetic spectrum, this is just a complete range of electromagnetic radiations arranged according to the increase or decrease, or just arranged according to um, wavelength or um, okay, arranged in wavelength increase or frequency increasement, something like that. So sometimes we write them as, you find some books written them like radio, micro, infravisa, then ultra. We have ultra, X, gamma, stuff like that. So my interest is not to actually write all this, but it's just to explain. All right. Okay. Let me just change the. All right. Okay. So that is it. So it is just the range. When you say electromagnetic spectrum, this is just a spectrum that shows a complete range of electromagnetic radiations, which include radio, microwaves, um, infrared rays, then ultra. I mean, I'm supposed to write ultra. So we have radio, micro, infravisa, ultra, X, gamma, stuff like that. I'm sure you remember this. Like, we have like the range of these electromagnetic spectrums. So they actually, it's just when you talk about electromagnetic spectrum, we have just the range of those radiations that we have. Those radiations such as microwaves, radio waves, and they start from gamma rays, X-rays, stuff like that. They goes like that. So those are what we call electromagnetic spectrum. It consists of those electromagnetic radiations, all right, that are arranged according to the increase in frequency or wavelength. So that's how they will be arranged. Then when we talk about how UV visible spectroscopy, so we are talking about now the atomization transition of electrons in the matter using this UV vis spectroscopy. So how do we determine the concentration? So UV visible spectroscopy is based on the absorption of UV or visible light, ultraviolet or visible light, by molecules. So once molecules absorb UV, um, they will be transitioning in those pi electrons, such as we experience transition, let's say pi to anti-pi, all right, then non-bonding to anti-pi, bonding like that. So these are just examples. Once molecules absorb, so the electron will transit from one place. These lone pair electrons, they will transit to such anti-bonding um, bands. So that's how the transition will be formed once these molecules or atoms absorb the UV spectroscopy radiations or just the UV radiation. So there will be an transition in the orbitals of these um, 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 there will be transition in these orbitals, and you will see electrons jumping from one energy level to another. So that is it. Then how do you determine concentration? So concentration will be determined using Beer's-Lumbers equation. What we need to know is that um, what we need to know is that since concentration is directly proportional to absorption, we have Beer's-Lumbers equation, Beer-Lumbert equation, which is given as A is equal to, this is the absorbance, then is equals to E, which is the constant absorbed value. Then we have the length of the cuvette, okay, the instrument where you put your atoms. Then we have also what we call the concentration now. The concentration now, you see. So concentration is direct proportional to the absorbance. So this means that we can also, so let me just like tackle this and I'll be able to actually solidify one or two things. Okay. So we know A is the absorbance. So A is the absorbance. So you need to be writing this like when you are writing paper. Then E, I said, is the molar absorbit. So this is just molar absorbit. All right. Then we have also the concentration. So it's just concentration in moles per decimeter. So that is concentration. Okay. Then we have the path length, or just the length of the cuvette. So it can be diameter or the length just in upward. So we say this is path length. All right, so that is it. Otherwise, concentration will be determined, since concentration is directly proportional to the absorbance. Meaning that measuring absorbance allows concentration, calculation of unknown substances. So we know this. So since we know the absorbance of substance, we'll be able to actually also tell the concentration, since this thing is direct proportion. So this is what I'm trying to say. Okay. So Beer's-Lumbers will give us the concentration in these organic compounds. So to calculate the concentration of these compounds, what I'm trying to say is we use what we call Beer-Lumbert equation, which states that absorbance is equals to absorbivity times path length times concentration. So we'll determine the concentration using the absorbance, because we'll see the absorbance of the molecule and the what is produced, and we'll be able to tell, to say the concentration was this so much. Okay, so that's how these are kept constant. So we'll be able, what varies the concentration and also the absorbance of the molecule, so which is just direct proportion. I hope you are getting the information that I'm trying to put across. All right, that is it about how to determine and what is an electromagnetic spectrum. So you write notes as much as possible. By the way, um, it, atoms will be absorbing um, UV, which is UV spectroscopy. So this ranges actually from should be 200 nanometer to 800 nanometer. So those are the information you can add just on the UV, since they have mentioned UV. So talk much about UV, then you'll be well and good. All right, that is it. Let's go to another question. Okay, the other question says calculate. All right, um calculate the lambda max for the following compound. So this is what we call, first of all, these are just normal compound dienes, and there is dienes. These are compound which has the conjugation like this. All right, so the conjugation is doubled like that. So now how do you determine How do you determine now the lambda max? So what we do is, first of all, you identify what compound is this. Okay, these are just normal dienes. So the best value that they'll get is what you call, what is the best value? Is this homoannular or heteroannular? You identify it like that. All right. So since this is just um the bonds are inside, all bonds are inside, so this is what we call heteroannular. Okay, it will get 214. If it's homoannular, it will get 253. So say base value is equals to 214. 214. If it was homoannular, is 253. So 214 nanometers. All right, I won't put this, by the way. So then first of all, you start the conjugation, let's say from here. 1, 2, 3, 4. All right. So there's an extending now conjugation. The conjugation would have just been 2 like that, like I demonstrated in the first page, in the first explanation, but now there's an addition conjugation. Okay. All right. So so there's that extended conjugation. So we extended conjugation will give us 30. So per each, under these normal dienes, extended conjugation should give you the value of 30. Then the other thing that we'll talk about is, here we don't consider alpha, stuff like that, but we consider about their Q groups under each was this double bond. So you can see at this point we have this methyl there, 1, and also here 2, and also here, no, here there's nothing. Then here we have 3, right? We have 4 there, then we have 5 there, right? And then 5, let me count. 1 there, we have 2 there, all right? We have 3 there, we have 4 there, we have 5 there, we have 6 there. All right, so these are the residues or ring residues, or just alkyls if you want to call them like that. They are just residues. So say residues, they are how many? They are 6, and each is getting the value of 5. So say 6 times 5, which is equal to, that is it, 30 nanometers. All right, then again we have what we call extended. I've already written it. Residues have. Then we can talk about now exocyclic bonds. So exocyclic bond, you're talking about a bond that will be exocyclic to the other. So the bond that is outside to the other, like this one. Here, this bond is extending the conjugation to that point. So this means that this bond is exocyclic to this one, okay? To this ring here. Suppose this is ring A, this is ring B. So A, it has exocyclic bond, which is that one, which is out of it. So that is it. It's extending the conjugation, but it's out of it. So we have exocyclic, let me say exocyclic bond. We have 1 there. All right, this one is extending again, this one is extending the conjugation to this bond, but this one is not extending any conjugation, you have seen. So this means that we have 2 exocyclic, because at this B there's also an extending conjugation from A. There's this one, and also at A there's also that extending conjugation. So we'll say 2 times 5, each conjugation exo, it is actually giving what we call 5 value nanometers. So that will be 10 nanometers. So to calculate lambda max, that will be, so these lambda max, these are just absorptions in the UV spectroscopy, but of the compound, because compound is a combination of atoms, so we can't just get direct atom, but we'll rather use these ones to actually come up with complete absorbance value of these wavelength. All right, the reason it could be maybe axons, but we just look at them and we'll see that it goes like that. So when you add these, I think you in punch on my calculator. All right, so that will give me 284. This is 284 nanometers. So this is the absorbance or lambda max. So we go to this one, these ones which are actually ketones or enones. So also we identify the base value. What is the base value? So base value for these enons, you look at enons, they have the base value of 215. All right. So they have the base value of 215, or the enon. Whenever you see this O group, just know that there's a base value of 215. From there, then you identify the conjugation. Okay, the conjugation is forming to that point. Then the carbon this is the functional group. So the carbon after this function group is an alpha carbon. Okay. The carbon after this, it's a beta carbon. If there was another carbon there next to that, that would have been what you call a sigma carbon. I mean a gamma carbon, then sigma carbon, goes like that. Okay. So that is it. So when you see that at alpha carbon there's a group, it's actually holding 10. All right. So that holds 10. So at alpha carbon, so there's 10, okay, value. Okay. If there were a lot of groups there at alpha carbon, would have said 2 times 10. That's the value it holds. So that will give us just 10 nanometers. Then when we go to beta carbon, at beta there's also 2. So at beta there's 2 of residues or substituent. So that will, at carbon, I mean beta will hold the value of 12. Then gamma and sigma, they'll be having 18. So this will say 12, that will give us 24. So when you add those two, you get your lambda max. Okay, so your lambda max now, it will be 249 nanometers. All right, that is it. So that is it about this. Make sure that when you see, let's say it was extending the conjugation, suppose under this we have something like this, then we are extending the conjugation like that, again the conjugation like that. So would have named this as alpha carbon, this is beta, this is gamma, then this is just sigma. All right, so this value, if there were other groups like that, or no groups, or let's say they are groups, so you say this one is having the value of 10, this beta is having the value of 12, the gamma is having the value of 18, and also the sigma is having the value of it. So you look at the substituent, then you multiply times the number of substituents that you have there. So that's how you'll be determining this under these enons or ketones. All right. So that is it. Let's go to something else. So the other question says, define sulfonation, mention the mechanism of aromatic sulfonation, 6 marks. All right. So what we need to know is that sulfonation actually is this is just an electrophilic aromatic substitution reaction in which this SO3, all right, is introduced into aromatic ring using the concentrated sulfuric acid or uric acid. So this will be introduced to the ring, and that will be what we call sulfonation. Sulfonation is just an electrophilic aromatic substitution reaction in which this group, this is the group I'm interested, is introduced into aromatic ring using the concentrated sulfuric acid. So it happens like this. So let me just introduce to you. So the aromatics, let me light the aromatic ring, and we are going to introduce this sulfonation, or this group. Okay, we introduce it like that. So this will form what we call now sulfonation. So the process of making this is what we call sulfonation. So sulfonation is just an electrophilic aromatic substitution reaction where we substitute this guy, in which this sulfate group, I don't know if it's sulfate or whatever, is introduced into the ring, all right, using uric acid or sulfuric acid. So that is it. Let me just demonstrate the mechanism. So the mechanism goes as follows. So say the mechanism. All right. So the mechanism goes as follows. One, formation of electrophile. So one, formation of electrophile. Formation of electrophile. electrophile, formation of electrophile. What do we do under this? We'll say H, the sulfuric acid that we had, um, it will now form, like, we'll change it into sulfate 3 there, and we'll say H2 there. All right, everything, there's nothing we have changed, everything is just okay. So this is the first step. The second step is now we have formed, this is the electrophile now that we have formed. So the second step that we are going is to attach on the aromatic ring. So we are going attachment of attachment, or attach on the aromatic ring. All right, so we attach this on the aromatic ring, and which basically benzene attach on the what? It's the benzene now attaching the SO3, forming the complex aluminum, will form the sigma complex. You remember this? So I'll demonstrate an example. Then from there, deprotonation. So remove the proton. So say depro. All right. So this is the mechanism that will happen. So first of all, we have formed that, and we have now S3. All right. Plus water. Then plus the same ring that I have. Let's say I have this ring. All right. This is a benzene ring, right? Okay, so what will happen is, this is the first step, formation of this one, I've done it. Then also attachment, I'm now demonstrating attachment on the aromatic ring. Then it will attach itself there. Then from there, after attaching itself, it will depronate the hydrogen, which is, there's a hydrogen there. Okay, the hydrogen is removed, and this is charged negative. So the hydrogen is moved as the negative, then this will be positive. I mean, the hydrogen will get negative, then this will be positive. So what will happen is that we'll have something like that hydrogen will be attached on the other side. It will bond like that. Then the sulfate also will attach there, and we'll have something like 3, then H there. The hydrogen is now there. This is just a sigma complex, because this can also go to the other side. So all right, so this is what will happen, and something like that. So we'll form something like that. All right, so that's how we'll form this. Okay, that is it. Otherwise, on the aromatic ring, so this is a benzene ring. If you want, you can write in this form, because there's a conjugation inside there. All right, conjugation inside there. Okay, so that is it. So you, like, get 6 marks. You explain to say one, formation of electrophile. From there, then attachment on the aromatic ring, then deprotonation. So after deprotonation, then you have the compound, this compound formed. So that is it. All right. So let's go. Discuss the chemical properties of argonolithium compounds with the following reagents. So we have the ketones. So discuss with the, so we are talking about now the properties of these organolithium compounds. All right, so we'll do those things. So let us now start with the ketones. So with the ketones, let me use the black pen. With the ketones, so what will happen is that we have lithium compounds. Let's say, so these ones are more reactive. they are more reactive. So what will happen is that, suppose I have also a ketone with R2, where this 2 is the number of alkyl groups again. So let me just differentiate by writing that. Then we have with this ketone, then what will happen is that always this one is more reactive, right? So since it's more reactive, it will replace it to go react with the more reactive element, which is the oxygen. So here we're going to have R2, all right, R2, the same way we have now, there's carbon there. So this carbon now, it will react. Now, since this one is more reactive, it will go to react with that one. So we say we have oxygen, lithium like that. All right. Then this other that we have, this one, the alkyl group from that. So that is it. That's what will be formed. That's how they react with the ketone. Then coming to the reaction with the carbon dioxide. So you have seen what has formed. You just, once they're reacting with the ketone like that, you just go replace this. This lithium will react with the oxygen, and this one will take it back there to the other side. That's, it will attack on the back side, on the forward side. So that's how it will happen. Then reacting with the ketone, I mean carbon dioxide. So we have a lithium there. I mean organolithium. Then we have that compound plus O2, carbon dioxide. So how is this going to happen? So first of all, we have first to actually um light the way it is, like everything. So like I said, we light R there, or is this our Q group. Then you come with the carbon the way it is. Then there's lithium there, which will be attached to the carbon, like I explained there. So we'll do a wake up for us to actually um, add, to depronate this lithium. So do a wake up reaction. We add hydrogen ion, then that will give us the carboxylic acid. Now form the carboxylic acid. So they form carboxylic acid is when it reacted with the carbon dioxide. So lithium. So these are the properties that you need to understand fully, that organolithium compounds, they react with carbon dioxide to form carboxylic acid. Or you just say, okay, this one won't be there, and the double oxygens will be there, and the hydrogen. So do a wake up for us to form this. Okay, that is it about this. That is it. That's how you'll be forming the carboxylic. Here you form an alcohol. All right. So it will be a tertiary alcohol if it is an alcohol formed. So that is it. That's how you form these compounds. Okay, thank you very much. Let's go to another question. So you explain things like that. So those are the chemical properties. You just demonstrate what is formed under these. Okay, so the other question says, light notes on the following concept. So where we have Fermi resonance. So I'll explain the writing. So what do we understand when you say Fermi resonance? So Fermi resonance, this is just the interaction between fundamental vibration and overtone combinations bands having the same energy or similar, and it resulting in band splitting and intensity change. So it will increase the intensity. So what I'm trying to say is this Fermi resonance, it will be the interaction between fundamental, all right, and um fundamental vibration and overtones, all right. So overtones, including the combination vibes. So what happens, this more like we have this combination, and we have this combination, and we have this band. So the first band, let me say V0, the second is V1, the third is V2, stuff like that. So the first energy, like this excitation, is what we call um fundamental vibration or fundamental band. Then the last, which will be coming, they are overtones. These ones, they are overtones, stuff like that. They are overtones. All right. So the first is fundamental vibration, V1, V0 to V1. This is the only fundamental. The last are overtones. Second overtones, first overtones, third overtones, stuff like that. Will be actually defining them like that or describing them like that. So that is it about the fundamental. And so the reason why these they are combining is to increase the intensity. So we'll find that the overtones, I mean Fermi resonance, it will be the combination of overtones, fundamental so the Fermi resonance is, resonance, it will be it is actually the interaction of fundamental vibrations, overtone vibration, and combination vibration of the same energy, because things only combine when they have the same energy or orbitals of the same energies, and it will result in band splitting and intensity change. So the intensity will also change, the band will also change, it will split because we have a lot, and once it is split like that, the band, then we expect more increase in the what? In the absorption of IR, which is infrared spectral or spectrum. All right. So that's what will happen. I'm explaining what is happening here, and you can deduce your own notes there. So Fermi resonance, overtones combination, it is actually the interaction of these three that actually makes up what we call Fermi resonance. As a result, we want them to be of the similar energy, resulting in band splitting, whereby increasing the light intensity or the change in the IR spectroscopy. That is it. Those are the short notes you can write there. Then, talking about Hooke's law, under this topic, infrared spectroscopy, which is the study of interaction which will cause a vibration in the molecules and rotation. Hooke's law also plays an important role in this IR spectroscopy band vibration, because the vibration, they follow the Hooke's law, which state that wave number is equals to the Hooke's law equation 2 pi c. All right, then we have k, which is the constant, then over, we explain this, which is the reduced mass. All right, that is it. That's what will happen. And once we see this, we'll find that we'll find that um, once we see this, we'll find that we'll be able to actually discover the force or the wave number of that particle. So wave number, it will be the inverse of wavelength. So what will happen is that um, this k is the force constant, so it's constant. All right, then we have this mu. All right, this means the reduced mass of that substance. All right, or a compound. So we're talking about the vibration now. All right, so strong bands will result in higher wave number. So wave number, the strong bands at least should be, as strong band increases, also there will be increase in the wave number. All right, so these are the, I mean, the direct proportion to each other. So as the bands absorb a lot, like high bands, like absorbing high wavelength, also the wave number increases. I mean, under this, as we have a lot of strong bands which absorb, I mean, the bands absorb higher, the wave number also increases. So that's how we can relate this equation. It's 1 over 2 pi RC K over mu there, like that. So that is the wave number. I mean, that's the equation. All right. Then wave number, this is just the number of waves per centimeter. Per centimeter simply means 1 over centimeter. What is this measured in centimeter? Is the wavelength. Okay. So wave number, it is actually this. So wave number is the inverse of wavelength. So wave number, we can say, is equals to 1 over wavelength. All right, so that's how we can divide, because this wavelength is measured in centimeter. All right, and we can relate this, the definition, to say it's just the number of waves per centimeter. All right, so this is actually, you define to say wave number is the number of waves per centimeter. All right, or it's the inverse of wavelength. So that is it about this. Okay. So question 6. So we are now describing what is an IR spectroscopy and mention various factors that affect IR spectroscopy. So to start with, IR spectroscopy, I can say, okay, IR spectroscopy IR spectroscopy, I can say this is just a type of spectroscopy that study the absorbance or the absorption of infrared, all right, infrared by molecules, all right, by molecules causing vibration transition, causing vibration transition. Okay, that is it. So IR spectroscopy, it will be this. So it will be the absorbance of molecules, absorbance of IR by molecules causing the vibrational transition. So that is it. So you can say IR spectroscopy is the type of spectroscopy that studies the absorbance or the interaction of matter with the IR radiation, okay, causing the what? The change in vibrational energy levels. So that's what you can say under this. You can even tell them to say, now let's talk about the now factors. Factors that affect this absorbance or vibration or transition, change in vibration, change in rotation are bond strength. So this bond strength, we have atomic mass, all right. We have also conjugation. So the conjugation also affect the absorbance of IR. So suppose we have this, I mean, we have that conjugation. Again, we have this conjugation. So the more we have these conjugations, the more also it increases the absorbance. So we can also talk about hydrogen bonding, dipole moment also. If there is dipole moment, it also increases the changes. So these are enough. All right. So strength, type of atoms, which is atomic mass, conjugation. Can also talk about dipole. All right. Dipole moment also affect. So those with the which are polar, they actually cause the intensity to increase. So polar molecules increase the intensity. That is it. So that's what we can talk about this. Under this, I've defined it. It's more important what I say than what I write because my handwriting is pathetic. That's why I've been feeling less to write all these things. Anyway, you understand this. You understand what I'm trying to say. So write a preparative method of aldehyde from the following reagents. All right. So how do we prepare this? The first one, I'll say, so prepare from primary alcohols. From primary alcohols, we use what you call mu deoxidation state, which is PPC. PCC. So what we do under this, we use what we call mu oxidation and from primary alcohols. All right. So what we do is we say we'll bring um we'll bring this alcohol, this primary alcohol. All right. We'll bring this primary alcohol. All right. So let me write this primary alcohol. Let's say ethanol. Then we actually put it in which is just mu oxidation, PCC. Then what we are going to form is the same thing, which is an aldehyde. So it is an aldehyde that we are going to form like that. So that is it. That's how we call it. This is under from a primary alcohols. What about from methyl cyanide? Under this, if I'm not mistaken, what we do is we perform the same methyl cyanide. So the condition that we use is we write SN chloride. All right. Then we need also to add some a bit of hydrochloric acid to form what we call um to form what we call um I don't know how I can name this compound. It's what normally comes out is CH. All right. Then NH like that. This is under methyl cyanide. So don't forget this stage. Very important. All right. So this is what we are going to form. Then from there, we just add some H2O to form what we want there, which is the aldehyde. All right, so that's how it will be formed. Then from ozone, so under ozone, we use what we call the same thing that I formed under, so under ozone, so I'll bring the ozone, I'll bring this, let's say, this compound, let's say ethene. So what I'm going to do is, I'll say I have R there, Q, then CH, then it's close to, I mean double bonded there with CH2. All right. So we perform with the ozone there, the ozone, and also a zinc as catalyst to undergo this reaction to form what we want. So that is it, to form the same alcohol now that we wanted. I mean aldehyde that we wanted. So those are the things. One, primary alcohols, you bring, let's say, ethyl, I mean methyl, then use what we call mu oxidation, which we use PCC to form this aldehyde. Then again, under methylcyanide, we light methylcyanide, we perform with SNC chloride too, like that, over hydrochloric acid. These are conditions that we perform with. So then we form what we call this compound, then we add some a bit of water, then we form our aldehyde like that. All right, so that is it. And also here, ozone, we add 1 2 3, which is propene, then we add some O3 there, then zinc will be able to form this. So what is important is to master the condition. These shouldn't be a problem, the cyanide and also is alcohols, so this shouldn't be a problem. So that's how we form these are the product formed. So last question now. So the question says, how do you synthesize alpha beta unsaturated aromatic acid by aldehyde condensation? So there's addition and also condensation. So to start with, this one goes like, all right, so this one goes like, so the first thing that we need to do is, okay, the first thing that we need to do is, we'll bring what we call a ketone. So a ketone, then we do a wake up. All right, so we do a wake up plus hydrogen, then what we form is a ketone like that, then added to some alcohol there. So say, I'll explain the mechanism. All right, then we heat a bit to do a wake up to change this conjugation. All right, we heat a bit to change this conjugation, and what we're going to have finally is this compound. All right, so the conjugation now of this hydroxide, we heat it to form water somewhere there. So what is going to be formed is the double bond there. All right, so the methyl was already there, so this is what we have formed. So I'll explain the mechanism why it's formed like this. All right, so the first thing that is happening is actually, the first step that we have is formation of inorate. Inorate is this anion. Now I'll explain the inorate. So it's formation of inorate. So always this condensation is formation of inorate. All right, then the second step that we do is the formation of let me do this. All right, is the formation of, I mean, nucleophilic attachment on the aromatic ring. So we attach, so attachment, let me just say an attachment, sometimes it won't be a ring. All right, then from there, then dehydration. So these are the basic steps. All right, that is it. So let me show you the mechanism now. All right, so what happens is that the mechanism, So the first thing that we do is, um, suppose we have the compound that we had there, all right, like that. So there is under this is what we call alpha carbon, because this is a functional group. This is alpha carbon. Then we have bonds like that, all right. So these are hydrogens, these are hydrogens, these are hydrogens, all right. So we perform some OH hydroxide there, all right. So what we are going to do is we remove this hydrogen will go there to form water, all right. Okay, so what we form under this, once I do this, it will be the same thing which is here. um all right, so remember, once I do this, I'm adding this OH there. Okay, I'm adding this OH there. I'm like trying to break the bond, and I'm going to have what we call, once I remove this hydrogen, it's possible that this hydrogen, this bond can be between this, I mean between here, or the same bond can be up there, all right. It's possible that this bond conjugation, because once I remove this hydrogen which is there, I attach it to this hydroxide here, it will be a positive, right, and this guy is negative always. So what will happen is that um that change, there is positive and negative. So the bond is possible that the bond will be here, the double bond, or this bond again, since it can also exchange there, this bond can also come there, and that will be charged negative. So what I'm trying to say is, it's possible that the double bond can be here or they can be here. So what I'll do is, it's possible also to have the bond like oxygen. This is oxygen, by the way. Oxygen. Then the bond can also be there. You see, this is what we call now. This is what I've formed there. When it is negative, when this one sacrifices that double bond which it had there, and the double bond comes there, then what will be formed is what we call inorate. This is where I said formation of inorate. All right. So I hope that makes clear. Once this bond is actually, the hydrogen is removed, it's possible that the bond that can come there, it can be between here or there. So that's what I'm trying to say. All right. So that is it. This is the formation of inorate. Then from there, okay, from there, then what we are going to step 2, what we are going to form is, like I said, so we have two things there. So we have this one, okay, having the double bond, this one which was there, and also plus there are two things formed, and also we have this one with a double bond on top there, like that. Okay, so here what we are going to do is, pay attention, we are going to do what we call a wake up. All right, so it's possible that here, this bond which is here, all right, remember this guy, when it gave this bond here, it remained a negatively charged. All right. All right. And also here, when it gave this one, it remained a negatively charged. So what is going to happen is that um, it's possible that this bond can join also with this bond. All right. So what will be formed now is what we call, so add the hydrogen, I mean the bond like that, then we have this. So this now they have combined, all right, they have combined like that. Then that means that we have this one which is the bond which was there, then also we have this. So you have seen, I've just combined this bond, now you attach those bonds there like that. Okay, so this what you have formed under this is what we call, there's a negative charge there, by the way. Okay, this is what we call outdoor addition product. So this is an outdoor addition. So sometimes you can say, write a mechanism on how to write, I mean how to prepare the outdoor addition. This is outdoor addition. Now we'll do what we call outdoor condensation. So how do we do this? We add the hydrogen wake up there. So we add the hydrogen, okay, to do the wake up under this. So once we add the hydrogen wake up, let me just demonstrate to say it will be like this. So adding hydrogen, wake up, we are removing this oxygen there, and that they remember there was also some hydrogen there. So we are going to remove this oxygen and add it to hydrogen to make water. So what do we do here? We'll say, because there were two hydrogen there balancing this. All right, so we'll add another hydrogen there to do a wake up. In short, we'll remove the hydrogen there. So what we are going to do is, once we remove the hydrogen, um, we are going to form something like, I will explain. So the interest here is to, once we remove this hydroxide, the water which is there, dehydration which I said, once we remove that, that double bond, it will come here and it will form a double bond like that, and will form finally like something like that. All right, so outdoor addition, it is where you just add these two. Then unsaturated, the alpha beta compound is what I've now formed here, which the question needed. All right, so this is an alpha beta unsaturated condensation compound. All right, so that's how you form this. So the question is, don't forget the question, this is what it required. So explain the mechanism. So we have explained using this attachment. First of all, formation of inert attachment, then dehydration, then you are done from there to form uh the same alpha beta unsaturated aromatic by acid method. So these are the things you needed to write, and I think the explanation also helped you to gather some information. Yeah, keep practicing. Thank you very much.